Yeah, let me let me see if I can hang up and reconnect with my main computer. I'm going to sit here for just a second. I think I can do it through two computers at the same time, and and that way I'll be sure that when I hang up on this one that it won't be. Okay, 1 second. It's giving me. Okay, so let's go ahead and start, and then when it does reconnect, I can switch over. Okay, let me see if I can switch over now. Hold on. Okay, I think it's about to let me join. Let's see, so it's saying the host needs to let me in.
Recording in
Okay, good.
progress.
All right, I'm gonna hang up on this. So Holger asks, why would sorting be a problem for smoothness? It's funny that you asked that, Holger. There's several of us that are not convinced that it directly violates the smoothness assumption. Doesn't have to. As I understand it, this is what is usually meant by people like Mccrary. Let me put this here. So okay. All right. So we'll do the typical drawings that we do with yeah, I'll do this as the counterfactual. Let's say that this is my best understanding of what's going on. Okay, so all right, so this is without sorting, right? So it's like, a little bit. Okay, so this is without sorting. Let me respell that correctly. All right, without sorting, so this is y0. So this is expectation y0 for x. This is the x, and this is expectation y1 for x. All right, so this is the potential outcomes. This is unobserved. And what we've got here is people with higher values of x. Right, this is people with lower values of x. And let's say that to become eligible for the treatment, you've got to have at least C0. So eligibility for the program requires x greater than C0. So these people are not eligible. Okay, so let's say that these people, what ends up happening is they begin sorting on the running variable. So we get these people here. They are changing. Oops. Okay, so these people have left. They're beginning to sort. So let's say that this group of people here sorted out. Now their potential outcomes have not changed, but instead what's happened is they're over here. Okay, they're over here now. Let's see, where would they go? They're in the treatment, and we're now observing, you know, some sort of value. So they're like maybe over here. They've been treated. And their true value, so they're not even over here anymore. So they've got some new X. So it creates this, how would I conceptually think of it? So there was this group of people here, they went over here. So we're not observing their, where would their Y0 be? Their Y0 would have been, what would their Y0 have been without treatment? Would have been over here. Yeah, that's right. It would have been like right over here because their outcomes are still these low things. Right. So if this is where they are with treatment. And this is where they are without treatment. Without treatment, but higher X, right? So that's kind of the key thing here, is that we basically just took these people that were here and just moved them to this mass right here. And so now you've got this kind of changed kink. Do you see how this kink has changed? So like, you know, let's see if I can get this without. All right, so now, you know, you've got basically this, and it's got this, it's both got like a gap here, and it's technically not, it's discontinuous now. So, you know, and then this up here, you know, ends up being like this. So what we've got is with the sorting, as I understand it, with the sorting, number one, units choose X equaling C0. So that's what they're doing. They're choosing to get just enough X to qualify. That's why they're all right here. Right, so we just basically moved them over, but see, we didn't change their outcomes. Their potential, the Y0 is the same, so they move over just directly, and now there are discontinuous breaks in expectation Y0X. Now there's discontinuous breaks because this is no longer, one, we have missing people, so there's holes, and then two, it's no longer got that discontinuous. So when you do this extrapolation, you're not sure, you can't be confident anymore you don't have smoothness, so you don't have the identifying assumptions needed to estimate those causal effects. So what you're stuck doing is, you know, you're at this point, Holger, I'm not really sure how to say it. You're extrapolating from this group. You're extrapolating from this group, but this linear trend, actually, it looks like it may not be that big of a deal. Okay, so it's probably going to depend on the functional form. But imagine if we had something like this. And over here, it would have done one of those. Now it could extrapolate all the way down here. So I think that what happens is, depending on the functional form, extrapolation may not be guaranteed to identify expectation y0 x. That's the main problem. Because we're no longer, see, the reason we needed that assumption, the reason we needed smoothness in the first place, we needed it because of the extrapolation. It was the extrapolation, the projecting beyond the support of the data that you're getting from OLS with all of its functional, with all of its polynomials. You're needing it to just, you know, be lined up with that continue, you know, you're needing it such that when you've properly modeled expectation y0, even though the data is not there, you'll be able to correctly estimate it because the functional form is continuous. So you model it correctly right there, it'll have an unbiased estimate of the expectation y0 just above treatment. But once we start losing units who are contributing to that expectation y0 below treatment, we don't really have the same confidence anymore that the extrapolation is going to match over here. I mean, the extrapolation, you could have, you know, we basically need, what we need is, we need for our OLS to continue to get this line right, because we're going to use that line to get this ATT. But now it could be all over the place. It could, you know, depending on what this I mean, for a linear function, it won't probably matter that much. But if it was not linear, if there was any kind of nonlinear, any kind of nonlinearities into it, simply by removing these, you could have projections that go way down here. Does that make sense, Holger? It really comes down to the role that the identifying assumptions are making. Okay, good. If it doesn't make sense, let's just keep talking about it in different ways. If you have a new question that comes up, again, getting back to it, we just go back to it. Okay. Oh, good. All right, great. So let's look at some code. I have the code that works in Stata. I have the code that works in R. I have the code that works in Python. So you should be able to do this yourself. It's really simple. So there's not a whole lot to go over because all that we're doing is running regressions. We're just going to be running regressions, and then we're going to be doing some of the non-parametric estimation, and that's it. So let me tell you about this paper. This is a paper that's probably worth investing in. Well, maybe not the paper, but definitely the chapter of the book. And the reason it's worth investing in is it's possible that this could be a really powerful technique throughout the continent of Africa, or even certain countries in Africa, depending on how many smaller jurisdictions are voting in your democratic elections. As you'll see, it's going to allow you to study a lot of things that otherwise are really hard, but they're about studying things that what this procedure is going to do, what it's really empowered to do is to study the effect of one political party on some sort of measurable outcome versus another. So if you think that in a certain country, there's certain political parties that have the reputation of, doing, having, in the United States, the Democratic Party is typically the one that supports more government poverty programs than the Republican Party, just to name one exception. On a lot of domestic policy, the Democratic and the Republican parties are very different. On foreign policy, I'm not positive they are massively different, but on domestic policy, they are very different. And so this is a study that was done to try to estimate the effect of the Republican Party on, the Democratic Party on some outcomes, but it's a little bit more scientific than your typical policy paper because it's going to try to get at a more fundamental question about democracy. So let me just finish this little cup of coffee here. It's called "Do Voters Affect or Elect Evidence from the United States House?" It was published in the Journal of Quarterly Journal of Economics by David Lee, Enrico Moretti, and Matthew Butler. So it's a very important paper. It's a very important empirical paper in the field of public choice, because it kind of establishes some facts about how democracy works and how legislators behave. But it also created the close selection design of an RDD. I call it the close selection design because it's like a version of, or it's like a very specific version of regression discontinuity. A lot of the papers people write, as you know, if they use instrumental variables, if they use regression discontinuity design, they just become applications of a particular procedure. What was different about this paper was it was so influential that everyone tried to copy the design. Studying, like we saw yesterday, I kind of briefly mentioned a paper that used the close selection design for governors. I've seen them used to study pollution. I've seen them used to study abortion. I have seen them used in African contexts. I just can't remember them off the top of my head. And that's because there's just so many of these papers. I wonder how many times it's been cited. I'm just curious now. Lee, Moretti, and Butler, Google Scholar. Uh, 860 times. That's a lot. That's a lot. So it's been cited a whole lot. Very influential. And part of the sites that are happening is that people are copying that design. So it's taken on a life of its own. We're going to take everything that we've done and just replicate the paper and learn a little bit more about the application. So in the field of public choice and in political science, there's two very different views of the role of voters in a democracy, in a representative democracy. One is that competition to get votes will cause politicians to compromise their positions in order to win more votes. Okay, so this is like a median voter theorem kind of belief. I'll sort of just show you what I mean real quick. So if you've got this line right here, you've got this line, and right here you've got liberal, and right here you've got conservative. Okay, and you've got this candidate here, and you've got a actually let me do it a little bit. Let's see, right is red, so we'll do this, and then here we'll go. Oops. Okay, so we've got these two candidates. All right, so we've got Biden and we have Trump. Okay, and this dimension here is their policy positions. We're just going to say like their policy positions on anything is can be simplified along a line. And this line represents, this is the, actually, let me say it a little different. So this is the voter policy positions, all right? So it's like, you know, there's some voters who are very, very liberal, and to get their vote, you've got to say liberal things. You've got to make promises in order to win these people. And so like all along here, we've got voters, okay? We've got voters all along this line. I'll just put them all in here. Let's just say they're evenly distributed. I don't, that kind of stuff is usually in the model, but I'm not sure if it matters for us. So right now, the people that are going to vote for Joe Biden are basically going to be these people, and the people that are going to vote for Donald Trump, they're going to be these people, okay? Because these people go to they go to their closest. Right, so they go to their closest. Right now, what that means though is that if Joe Biden could just move to the middle, if he could just move to the middle, watch what he can do if he can move to the middle. I'll move this. So if he can just move his policy position, so maybe he becomes slightly more conservative. He becomes slightly more conservative. Oops. Now look, as he does that, as he moves and becomes slightly more conservative, you know, so now he's here, what is happening? So he's getting all of those people, and now he's getting all these people, because now, you know, actually that doesn't look exactly right. Let's see. So it looks like he'd probably get right here. Let's see who you get. You get, so it looks like right there. Get right there. And then Donald Trump would get those people. So he's going to become more, as he moves though, as Joe Biden moves. Okay, he's going to move like this. He's going to gain those people. And he's going to allow some more of these people to come here. But notice what Joe Biden's doing. Joe Biden's becoming more conservative, all right? Well, Donald Trump doesn't want to lose these voters because he wants to win. So what's Trump going to do? He's going to move. In this process of moving, I'm going to get rid of these red things. So this process of moving continues until they're holding the same views. Okay, and that's called convergence. Convergence basically says that the competition for votes causes the politician to move to the center. All right, so the competition for voters' votes will cause the politician to moderate their views, their policy views, in order to win votes. This is called the median voter theorem. It's by Anthony Downs. All right, and you'll do it. So it's kind of related to the median voter theorem anyway. So you'll continue to moderate your policy views, and in equilibrium, the funny thing is, in equilibrium, each politician actually will behave the same. It won't matter who wins, because the competition for votes caused each politician to behave the same. So one of them wins, but they would have both behave the same. We just don't observe the loser behavior. Okay, so that's the media, that's what Lee, Moretti, and Butler call the convergence hypothesis. Competition for votes can force even the most partisan Republicans and Democrats to moderate their policy choices. In the extreme case, competition may be so strong that leads to full policy convergence. That's full policy convergence, okay? Full policy convergence. Opposing parties are forced to adopt identical policies, right? Implications of that are kind of interesting. It doesn't really matter who wins. That's the way I usually think of it. Doesn't matter who wins because they're each going to behave exactly the same, right? Let's put them back. Versus divergence. And in divergence, in divergence, voters are picked. All right, so we'll say that Biden wins, Trump loses, Trump's gone, and Biden just continues to behave the way that he would have behaved anyway. So under divergence, the distribution of voter preferences in an area doesn't influence the choices of the policies that the politician pursues. Politician has her preferred policies, and when she wins, those are the ones she pursues. Okay, so this makes predictions. If we could compare the policies of a winner to, if we could compare the policies of a Bear winner to a Bear winner Democrat to a Bear winner Republican, convergence says they'll vote the same. Divergence says they'll vote different. How do we test this? Using the close RDD design. Using the close RDD, we will compare politicians who each got 0.51, 51% of the vote share, but from different parties. If there is a jump in their behavior, we know divergence, we know we can reject extreme versions of convergence theory, right? If they are the same, then we can reject extreme versions of divergence theory. Okay, so that's what we're going to do. We're going to do that. We're going to see what they find, then we're going to try to replicate what they find. So it's very difficult to test these since you don't observe the counterfactual votes of a loser for the same district time. So we don't observe what you would have done, what the loser would have done in that with that. We don't have overlap, of losers that got 51% of the votes. By definition, in the United States, because of the majority voting rule that's used to determine winners, which is 51% or more, we don't observe what the behavior of somebody who got 49% would have done had they gotten 51. Lee, Moretti, and Butler developed a closed selection design to choose between them. The metaphor of the randomized control trial is helpful here. Maybe in these close selections, it's being determined by a bunch of random chance. A few votes here, a few votes there, maybe some traffic stopped some people from coming, maybe the weather mattered. There's a bunch of randomness that might be going on. So what are we going to look at? We've got to have outcomes. So let's just review what we need here. The data we need, outcomes of politician behavior, 2, running variable, 3, determining running variable determining treatment, 3, treatment, 4, cutoffs. Right? So you need all 4 of these. All right, you need all 4 of these. So what we're going to do is we're going to get outcomes from the liberal voting. We're going to get a liberal voting score. So in the United States, I don't actually know how it is in Africa. Obviously, I've actually never been to Africa. I hope to visit one day, but I've never been there. So, and I don't know a lot about the continent. But in the United States, there's this, ongoing thing where small organizations will basically build these report cards on how politicians vote. So for outcomes, we will use a report card on politicians from the Americans for Democratic Action. They scored politicians based on their votes. Thank you, Angelica. I look forward to meeting in person then in real life. They scored politicians based on their votes. So the context that we're going to look at, we're going to be looking at the House of Representatives elections. In the United States, we have the executive branch, which is the president, police. We have the legislative branch of government, which is Senate, Congress. They make laws. They enforce laws. And then we have the judicial branch. This is judges, and they interpret laws. And what we're going to do is we're going to focus on this. We're going to focus on the legislative branch of government. All of these have elections. We have, all U.S. branches of government have at some levels elections. Okay. Most, if not almost all, use the majority rule to determine winners. 50% or more votes. All right. So that's what we got. And we're not going to look at the executive branch because we need a lot of data. We don't have enough presidential vote. We don't have enough presidential elections to do it. So remember, the data requirements for RDD remain large. We need a lot of elections because we need a lot of close elections. All right, we need a lot of elections because we need a lot of close elections. Only with having the universe of elections are we going to have enough mass at the cutoff. Okay, so that's the thing to keep in mind. Even though you don't necessarily need all that data, all right, in print, theoretically, you don't need all that data for identification. You are going to need it for estimation. All right. So for identification, it's all at that limit. It's all at the cutoff. But for estimation, because you're doing all that extrapolation, you need all the data. Just remember to keep that in mind. Because you're doing extrapolation, you need all the data just to identify the causal effect at the cutoff. This is something you have to remember. All right. So we can't use the executive branch because we don't have enough elections. All right. And America's only, 250 years old. We don't have enough. We've only had 40 presidents. It's like 80 elections or less than that. So can't use that one. Senate is elected every 6 years. So that one's that one's fine. We have an old country, but every 6 years we only have 2 senators per state. What we have instead is the House of Representatives. Politicians serve 2-year terms. They come up for re-election every 2 years. Senators come up every 6 years. All right. So we have more House elections, and the House represents regions, small regions. So you may have, I don't know. Well, I'll look. I think we may have, I think we have almost 500 congressmen from the House. We have 100 senators, and I'm now curious. Actually, I'm dying to know. I've got to know. So let me. How many do we have? How many congressmen in the House? I think it's 435. 435 voting representatives. So we have more of those. So that means that, and we can't use the judicial. I mean, you could use, so interestingly, you could do a study. You could do any study using the close RDD so long as you had enough elections. So you want to choose politicians who serve either shorter terms, more elections, or hold on. What'd you do, kitty? Oh man. Pretty sure my cat just, oh no. Okay, I'm gonna have to, my cat just lost my stylus, so I'll have to come up with a solution in just a second. I'll look at our break. So you're either gonna have shorter terms or a lot of politicians, more elections. That's that's what you want to think about. Pick the environment where you have enough data. Okay, that's what you're wanting to do. You're wanting to pick the environment where you have enough data. All right, and for this, that's the House in the US for this. Okay, that's the House. So they're going to use the ADA scores, all right, for all US House representatives. For each Congress, ADA is going to choose about 20. ADA is the name of the organization. It's called Americans for Democratic Action. ADA is going to choose about 20 high-profile roll call votes, and a roll call vote is when the Speaker of the House, the head politician, will call on the politician and ask how they want to vote, yay or nay, right? And then it's recorded. The ADA is going to take 20 of these votes every year and score which one is a liberal vote and which one is a conservative vote, and assign those points to the politician. The more liberal votes a politician gets, the higher their ADA score, because the ADA is a liberal organization, so they're counting votes in terms of overall liberal voting. If it was a conservative organization, it'd be the opposite. Okay. Vote share. All right. Remember, we needed outcomes and we needed a running variable. It's going to be, so what you've got to do for these studies, for these close RDD, close election RDD, you have to have a running variable. You always need a running variable. Running variable determining treatment. You have to have a running variable. And for democratic elections, it will be some running variable, some measure of total votes. But since winners are determined by the share of total votes, usually the running variable will either be vote share, which will be a percent, or margin of victory, which will be net votes for winning. Okay, so either one is fine. There isn't a right or wrong, because if your vote share is 0.51 and your margin of victory is positive 10, they both mean you won enough. So keep that in mind. You'll need total votes for the election, total votes for each candidate, and transform the votes for the candidate into a percentage. Probably vote share is the easiest one that readers will immediately understand. That might be the one to use, but Bland 2015 uses margin of victory. Doesn't matter. Lee, Moretti, and Butler 2004 will use vote share. It'll be votes, total votes times 100 to get a percent. Okay, that's what it's going to be. Running variable is vote share, share of all votes that went to a Democrat. Okay, they're going to use the close victory, check whether convergence are very, all right. Discontinuity, vote share equal 0.5. All right, so this right here is the rule. This is the cutoff. Okay, if the Democrat wins more than 0.5 of the vote, then the Democrat wins. Otherwise, the Republican wins. And I've got several do files and several R files that will implement this estimation. You can go along with me in just a second. So here is table 1, all right, from the paper. This is the main results. Main results are global regressions. All right, actually, no, let me take that back. They are local linear regressions. What does that mean? First, they're only using a portion of the data. Total sample size, I think, is around 13,000. 13,000 observations. Okay. But they're using a sample of 915. Why? Okay, notice, why did I highlight this? They use only the elections where the winner, where the outcome was determined by 48% to 52% vote share. They drop for their main analysis the elections where people won, where Democrats only won 47%, 40%, 55%, 60%. Okay, they're going to drop those. They're going to instead estimate linear local regressions. No covariance. Okay, no covariance. All right, here's what they find. This is their finding. We're going to ignore this stuff. All right, what does this one mean? Column 1. The effect of electing a Democrat, just barely winning, on future liberal votes, T+1. So this is the politicians' voting behavior in the future, having just barely won in the past. Column 2, same as column 1, only for the year they win, T, not T+1. And then column 3, the probability they win the next election having just barely won the first one, the first election. This is a measure of incumbency. It's thought that incumbents are the politicians who were already a politician when they ran for re-election. Okay, so Trump was the incumbent because he was running for re-election. Biden was the challenger. So this one right here is a measure of the likelihood that a politician wins again, having just barely won. Now, remember, keep in mind what this study is about. Keep in mind what this study is about. If a Democrat is winning the election just barely, because at such close elections, winners are being determined randomly or smoothness holds for these close elections, right? Then the coefficient on Democrat has a causal interpretation, not a correlational interpretation. The RDD design eliminates the selection bias. Okay, it's no longer measuring simply that Democrats were being elected by predominantly Democratic communities. It's measuring the causal effect of electing a Democrat, ignoring the voter preferences in the communities. Okay. Under convergence, the coefficient would be 0. Under divergence, it would be positive. And it's positive. All right, it's positive. So column 1, elect a Democrat, and she will vote 21.2 points higher on the liberal score than the Republican who just barely won in his election. Okay, so that's the first thing. So the control group is the Republicans who barely won themselves. They're getting the 0.49 vote share. That means, if a Republican won, it means the vote share was actually less than 0.5, because vote share is measured as Democrats winning. All right. Column 1, more liberal. Column 2, 40 7.6 points higher on a liberal voting scale. Column 3, bare Democrat winners are 48% more likely to win again in T+1. So there's lots of really interesting results. Overwhelming evidence for convergence. Overwhelming evidence for convergence and incumbency advantages. Overwhelming evidence for convergence and incumbency advantages. Now, Hahn, Todd, and van der Klaauw emphasized using local polynomial regressions. They emphasized using local polynomial regressions, and you can use non-parametric methods too that will estimate a functional form, or sorry, they'll estimate. You can estimate expectation y of x just using histograms or using fan regressions or things of that nature. So that model would be something like this. We're going to look at that. So we'll do this visually. We're going to estimate the average liberal score across the running variable. All right. So it's just going to be taking averages for certain bins. Now, my students have programmed it in R so that it'll run in R. But there is a command that I learned from Marcelo Perdillo called Cmogram. And I forget the author's name. It's in the book. And it has a lot of useful options, though many people prefer to graph their pictures themselves, kind of program it themselves. Cmogram is nice in Stata because it just kind of does it instantly. It just has an automatic binning feature. So Cmogram is a user-created Stata package. And when you use it, it will visualize expectation AEA along the vote share. Okay, it'll visualize it, but it will automatically bend the data. You can't choose your bins. It's using some algorithm for choosing the width of the bins for each data point representing E80A vote share. So if you want more control over your binning, you will want to use your own modeling or another package. All right. But I'm going to show us Cmogram and the R code for its own visualization. All right. So we're going to recreate. Yeah, Angelica, I'm going to show it to you in 1 second. I'm going to show you it's all in the public domain. It's all on GitHub. Give me 1 second and I'll show you. So we're going to recreate these figures. Now here's the figures. This figure was column 1. This is the column 1 result. Notice the y-axis says ADA T+1. This is the liberal vote along the vote share for the election year after the first election. So 2 years later. Okay. And this right here, this is that 20 points higher on ADA score. Okay, there it is. There's the gap. All right. So this right here is Republicans. This is Republican voting. This is Democrat voting. You know, Republicans are going to be in the smaller vote share because if a Democrat won 25% of the vote share, Republicans won 75%. So this is all situations where vote share favored them. All right. And this gap is the causal effect. So the gap, it looks like it's called gamma, is the estimated local average treatment effect of a Democrat win in the House of Representatives on voting scores in T+1. No evidence for divergence. For convergence. Only evidence for divergence, at least not for extreme versions of, at least not for extreme. We can reject extreme versions of convergence. Okay. This is the column 2. This is the column 2 result. When you elect a Democrat, you will cause liberal voting scores at the margin to increase by 45 points. Okay, causal under smoothness. And then this is column 3. The probability that the candidate wins the next election, having just barely won the first one. If you elect a Democrat, there is a 48% higher chance she will win in the next election. Causal, not correlational, because in these close elections, the voter preferences are not the reason for the win. The voter preferences are the same in the vote shares of 0.51 and 0.49, presumably. Okay. So we want to make these pictures. We want to make the pictures, and we want to make the tables. So what we're going to do is we're going to go to CI Workshop. We're going to go to Master Do Files. We're going to go down here to LMB. All right. So you're going to want to pull up LMB 1, 2. We'll pull up LMB 1. All right. So LMB 1, got to install some stuff. I always forget that when I load up R. So it's going to have to load some stuff. So let's look up this data, because I don't know exactly what everybody has. But let's look up LMB 1. All right. So LMB 1 here, Angelica, is the data. It's at GitHub. So either you can use the this command here, read data, using the full path command. Just copy this. It's stored at GitHub. Oscar says, is it a quasi-experimental research due to how they can obtain the data? Correct. It's quasi-experimental. Quasi-experimental just means that the researcher is not controlling the creation of the data. So it's quasi-experimental in that voters are voting, not the the voters are voting. So you're just collecting data from public records. And Melba asks, is it a fuzzy RD? It is not. They're not going to analyze it as a fuzzy RD. Reason it's not a fuzzy RD is because you cannot be a Democrat politician unless you win 51% of the vote. Okay, so there are no Democratic politicians that won 49% of the vote, and there are no Republican politicians that lost 51% of the vote. So so it doesn't it's not fuzzy, it's sharp. Okay, so fuzzy is always fuzzy is a situation where you can have the treatment below the cutoff. All right. So like in the United States, you have to be 21 years old to legally drink alcohol. I started drinking alcohol when I was 15, right? It was illegal, but everyone in my high school drank, or no, not everyone. Many students drink alcohol before it is legal. Probably the same in Africa, right? In parts of Africa. So you need fuzzy RDD for alcohol because treatment occurs below the cutoff. But in a close RDD, it's sharp. The reason it's sharp is because the treatment cannot occur unless X greater than C0. You cannot be the politician unless you win 51% of the vote or more. Okay, so that's what makes it, that's what's going to make it sharp, right? So we can look at this. So let's run this real quick. I'm not a big fan of the output of R, but let's look at it. All right, so here we're going to run this first regression right here. Now look, we're going to subset the data by you doing these local linear regressions. We're only going to look at the Democratic vote share from 0.48 to 0.52. That's column 1. That's column 2. That's column 3. Here we go. 21.28 for column 1, 47.71 for column 2, 0.48. So it's not exactly right. If you look back, all right, 21.2, 21.3, 47.6, 47.7. But it is right. Let's see if I can get a count of the number of observations. I don't see the count of the observations. So let's look in Stata. Stata will spit out the spit the data out. 915 observations. So I don't exactly know why it's not exactly right, but it's close. Can you not see these windows, Oscar? Can you not see that? What do you, Oscar, what do you mean by check the size of R windows? What does that mean? Oh, okay. All right, so it's working.
Excuse me, Prof. Can we see it a little bit? Is it possible to make the writings a little bit bigger? On our side, it's very small. I don't know whether it's only me, but it's very small. The font size.
Oh, the font size. Okay.
Yes, very small.
Like that? Is
Yeah,
that better?
That one is better. Yeah.
Okay.
You.
All right. And then for Stata, I'll where'd it go? Here, I'll also have I'll make it larger also. Okay. So you see how I made it? If it's okay, I'm going to work a little bit with the Stata just because, well, I can do both. All right. So I'll do both. So, so really straightforward that this is a local linear regression. All right. It's a local linear regression. You're just going to regress without covariance or without any, you're not controlling for the running variable. All right. You're not controlling for the running variable. You're just limiting it to a small part of the running variable, all right? Now let's look at everything. Now this is not a local linear regression, okay? This is not a local linear regression, uses all the data, right? So it's estimating it. Let's see what we get. Okay, results change a lot. They're bigger for LM1. That's column 1. They've gotten bigger. They're not so different from column 2. In fact, one of the things that you'll see here is that the column 2 results don't change a ton, but this probability changes a lot. So, you know, depending on what specification we use, we get very different things. Maybe zoom in. Okay. If it's a local linear regression, Melba says the estimate is a local average treatment effect. It's actually always a local average treatment effect, Melba. If you go back to the definition of the if you go back to the definition of the parameter. Okay, so let's go back to what exactly is the parameter that we're estimating. Let's go back to the very beginning of it when we defined the parameter. Here, notice what the parameter is. Okay, so this is the parameter that we're identifying. It's an average causal effect, but where is it? Where in the distribution of the what causal effect is it for? It is for units at the cutoff. Okay, so it's right here. Right. So this is a late. It's the causal effect only for those units whose treatment status changed when X passed C0. It is not for the units with large values of X or small values of X. Only for X equals C0. Okay, so the estimation method we use is not what determines which causal parameter it is. We are always trying to identify the average treatment effect at C0, which by definition makes it a late parameter. Makes it a late parameter. Does that make sense? It's a little subtle. It's a little bit of a subtle difference, but it's technically we are always estimating a late, whether we use local linear regressions, global regressions, non-parametric methods, kernel regressions, whatever. We are trying to estimate ATE at the cutoff, and that's a late if we have heterogeneous treatment effects. Got it. Okay, good. All right, so we have here global regressions. We can look at a recentering of the data. Okay, so here we're going to take our democratic vote share. We're going to subtract out 0.5, and we're going to get a democratic vote share underscore C. All right, and we're going to get, we're going to run 3 regressions here. We're going to regress score onto our treatment variable, and then we're going to control for our running variables. This is the first time we've controlled for our running variable. All right, so first time we controlled for our running variable. Look over here. There is no running variable in here. Notice that. The running variable is called vote share, dim vote share, or dim vote share C. We haven't done either. Okay, so here is the coefficient of interest, lag dim vote share. This is the running variable. This is basically the slope of the running variable. This 0.7725 just means that on average scores are rising. 0.7725 liberal vote points for every 1 point change in the Democratic vote share. All right, doesn't have a causal interpretation. This one has a causal interpretation under smoothness. And we've got a number different than what we found before. We had a 0.48. Here we're finding 0.58 under ADA T, and then we have a 33 under T plus 1. So they're different from each other, but they're not like what we found before. And the question really is, well, what's the right answer? You know, what's the right answer? And the right answer is, well, you can see it's very sensitive to what what answer we're getting is very sensitive to which data sets we're working with, whether we're working with the full sample or the local sample, whether we're controlling for the running variable, whether we are interacting the running variable. So notice this one. This is the proper specification. You always want to interact. If you're not going to be working with the local linear regressions and you're going to be doing those global regressions, well, then you're going to want to be interacting the running variable with the treatment variable. And that's what we're doing here. We're interacting the running variable with the treatment. Okay, summarizing it here. Let's see what we get. $30. I think it was 20. I think it was 20 before in the picture in their preferred results. We don't get 20 when we use the global. Now remember, in theirs, get it here. In theirs, remember, they're working with 915. We are working with 13,000 right here. All right. So we get a 30 on the T plus 1. We get a 55 on the T. They get a 47. So we're a little closer using globals. But and now the incumbency one, 0.48. 0.53. So it's similar, but it's not exactly the same. Okay, so that's LMB4, so I need LMB5. All right, so now we're going to do the same thing here, but we're going to work with a nonlinear function, because if you remember, there's a lot of nonlinearities in this, and if we didn't model the nonlinearities, well, maybe we get this and this, right? So maybe if without controlling for the nonlinearities, we're going to get some sort of biased estimate. Oscar says, can you show the table of data? Yeah, I can show the table of data. Is it okay if I show it in Stata though? Because I don't know how to do it very well in R. So let's look at the data editor here. So we've got states, incumbency, dim vote, and we need dim vote share. It's somewhere. There's a lot. Here's dim vote share. Okay, so we've got this dim vote share here. We've got the lag dim vote share. That's the T minus 1 dim vote share. I don't know what these are. Here we go. It's the year of the ADA. These are going to be used for the balance tests. Here's the score. Here's the lag score. The ID is a district. It's a ID variable is a district. It's the jurisdiction for the election itself. So if the election happened in my town, Waco, Texas, there'd be a variable. Let's find it. ID right here. So this is numbering the district. So you've got these districts. I just type it in here. Do I say LMB? Like that. What did you want me to look at, Oscar? Or Oscar, you wanted me to look at that? Okay. What did you want me to look at? Is that enough? Okay, that's fine. All right, great. It's both, Melba. It's basically the universe of elections. It's every single election over 1946 to 1995, and it will include people that were coming up for re-election, and it'll include elections where there's a incumbent, and it'll include elections where it's two people who had not been politicians before. It'll be both. So LMB5. Okay, so it's going to keep doing it, right? You got what you have here is what I did here was I had an interaction with a nonlinear vote share specification. Look here, I've got interactions. I've got the level vote share running variable, and then I got the square. So I've got this second order polynomial. So I'm going to now allow for something like this, right? This is actually not exactly a quadratic, but I'm allowing for, you know, a higher order polynomial, so I can fit this a little better, you know, hopefully. And getting close, I got this 0.52, 55. So it was 48 before. This is 30. So this is the first time we've kind of gotten this close to their preferred results. I'm actually cluster. Yeah, it's cluster robust. I'm not doing the, it's cluster robust, allowing for serial correlation at the district level. You can do robust standard errors. What I'm not doing is the honest confidence intervals. I'm not doing the honest confidence intervals that Colasar and Roth have done that I mentioned, but I'm correcting for you know, arbitrary serial correlation at the level of the election, which will be robust to heteroscedasticity. So that's what this clustering here is doing, as I understand it. In R, that's definitely what it's doing in Stata. All right, so we do here, we go LMB6. It's just going to do it again. Whoops, sorry. So let's go now. Let's see if I think I'm going to start moving into pictures. All right, so now I'm going to aggregate the data and I'm going to plot it. So let's plot the data, creating those figures. If this doesn't make something, all right, so look, So look what I did. I did it for the t+1. So this is this one, right? It's the same thing here, but notice this is a linear fit. And because this is a linear fit, it's getting larger estimates than this. So, you know, right here, they are not using the linear fit. If they had been using the linear fit, then they too would be getting something like this because it's influenced by outliers, right? But we're not. Right? So let's look at let's look at the quadratic fit. Oh, shoot. All right, this one I'm going to have to do in Stata. Here. Let me show you this in okay, so we'll look at this one here. There's the fit. Here's the fit. I think in R, I think what I did was probably, oh, here it was. Here it was. LM. It's probably this one, right? Is that what it was? Yeah, that's what it was. So you use the linear model, but you fit this polynomial. You did it like that. And it goes on and on. Here's the lowest. Here's how to do the lowest one. Then we can also do LMB9. This is going to use the RD robust command. If I got install. When we use the LMB robust command, it's going to use all of the data. Notice here, 13,577. Not positive why I dropped 11 of them, but it's going to use all 13,577. But it's going to do these local polynomial regressions with kernel weights. Okay, triangular kernel weights. So it's going to use this triangular weight, right? And notice now we get the 40, we get 46.4, 46.5, which if we go back, that's what we were getting using the local. Okay, so notice when you use the RD robust, it uses all the data. It's performing a lot like the local linear regressions, only it's using kernels, triangular kernels that weight the observations closest to the cutoff the most. Okay, and then runs local regressions, local regressions across the running variable. And we get, and that this is using a package called RD robust, which was written by Cataneo et al. I can't remember the exact year, but it's it was one of many of these authors' contributions to RDD. Let's figure out how to do the Mccrary density test and we can be done. Here, we're going to use the RD density command as well as the RDD command. We're going to use both of them. So let's let this finish installing. Look at that. It made the Mccrary density test. It's not really called the Mccrary density test at this point because it's a specific type of density test that Colonico and them created, but it's in the spirit of Mccrary's original density test. His original density test followed a very specific kind of binning and a very specific type of estimation, but Kalanick and them updated it. But still, right here, you're seeing no evidence for sorting on the running variable, okay? So in conclusion, Coffey and Second, in conclusion, the paper was very influential. There has been one paper that challenged it. It was by Coffey and Second, 2011. They were not challenging the research design. Nobody has a problem with the closed selection research design. They had a problem with the using the House of Representatives. But then others have studied it using over 40,000 close elections around the world, including the House from other time periods, mayor races, other types of US races, 9 other countries. You don't see the same problems as you saw with the original. So they couldn't find another instance where that critique applied. So assumptions probably hold. It's one of the best RD designs that we have. Okay. So let's take a break. It is it's an hour and a half into this. Let's take a 10-minute break and we'll come back at 40 minutes on the hour. And I'll see you in just a minute. Okay, I got to find that stylus that my cat just lost right in front of me. Oh, here we go. Okay, so let's go back in. So regression discontinuity in conclusion is a very important estimate, very important strategy. Highly recommend you invest in it. Something you might look into is that close selection design. I always am thinking that there might be lots of opportunities in African countries where that's never been applied. Maybe it has been. I know, but it might not be. It's definitely something worth reading. It's definitely something worth studying. You never know that something like that might come in and be really useful for you. But now what we're going to do is we're going to talk about instrumental variables. See, today's a Wednesday. I wonder if we went into difference and differences, then synthetic control, then came back to instrument variables. We can do instrumental variables. We'll do instrumental variables. I do want to save enough time for diff and diff, but let's go ahead and do IV. So instrumental variables is designed for situations where the kind of endogeneity of the treatment variable that you're faced with can't be resolved with selection on observable strategies. So an IV situation is one. Some causal questions you have are not going to be resolvable using controls or even RDD. Maybe because even after an RDD, the treatment is still endogenous. Okay, so what do we mean by endogenous exactly? And why does IV solve it? Why does IV solve it? So let's look at that. All right. So instrumental variables offers a chance of recovering causal effects of some treatment on an outcome. And the best instruments typically are going to come from your deep knowledge of the institutional details of the thing that you're studying. Really, the best research designs, if I could just say this real quickly, the best research designs, the best research designs come from a situation that you are already very familiar with. Usually what happens is your familiarity causes you to notice strange opportunities for causal inference that would otherwise be simply impossible for a stranger to notice. Okay? That means instrumental variables is really something that an expert can take great advantage of, because experts are deeply familiar with the phenomena being studied. There is no such thing as naive causal inference, not successful causal projects anyway. All causal inference requires, expertise, not just in the statistical estimator, but in the phenomenon you're studying. It's sometimes called domain-specific knowledge, and I oftentimes say institutional details. Okay? And I'll try to convince you about why that's the case. Okay? So oftentimes the reason why that is because so many times instrumental variables, not always, but a lot of the times instrumental variables will really leverage natural experiments. It'll really leverage natural experiments. And sometimes, to know how to take advantage of a natural experiment, you really have to already be invested in the work itself. Okay, so just to summarize, there are at least 6 different situations that I could think of where you might use instrumental variables. You think that you have omitted variable bias. Instrumental variables is a solution to that. You think that you have measurement error in your treatment variable. IV is a solution to that. You believe that you have simultaneous determination of outcomes and treatments by some, multiple equation kind of simultaneity problem, like a supply and demand question. Quantity and prices are determined simultaneously. You can use IV. If you have reverse causality, you can use IV. If you have a randomized control trial with non-compliance, you can use IV. And if you have a fuzzy RD, you can use IV. These are just some of the, conceptual problems that make IV very attractive. Now, this is an example of a picture kind of illustrating. This discusses a lot of, jargon or a lot of strange words. We haven't discussed these directed acyclic graphs, but just kind of follow me on the graph here. You've got here a treatment variable and you've got an outcome. You've got this treatment, you got an outcome, you got a causal path, but you've got some unobservable, and it causes D to change and it causes Y to change. In a picture like this says that D and Y are correlated because of U, not just because of causality. When U changes, both D and Y change, and therefore U causes a spurious correlation between D and Y. Okay, so in that situation, because U is unobserved, notice here this dashed line means U is not in your data set, unobserved. This is an instrument. Okay, this is an instrument. An instrument description, simple description of an instrument, instrumental variable. 1, Z is the instrument, and it causes D to change. 2, Z is not connected to U, the confounder, or Y, the outcome, except via its impact on D. That's it. That's all instrumental variables is. Use a third variable to move D around in ways that has nothing to do with U or Y directly. Then use that variation in D that was caused by Z to estimate the causal effect of D on Y. It's a very simple, very simple, very intuitive idea, but estimators can be hard. Can be more complex. We will discuss both the intuition, the practice, the art, and the estimation in detail. Okay. I'm going to skip its history, even though I love going into that. So I want to just put out here a couple of points here. There's two kinds of treatment effects. There's situations where treatment effect is the same for every person, constant. Treatment effect may differ for different people, heterogeneous, right? IV's interpretation depends on whether treatment effects are constant or heterogeneous. We will start with constant to learn two-stage least squares and issues like bias. And then we will introduce the heterogeneous concepts. Okay, then we'll go like that. All right, so that's what we're going to do. So constant treatment effects, everybody has the same treatment effect. Therefore, the ATE, the ATT, the ATU, they're all the same because it's all aggregations of the same constant treatment effect. If the treatment effect for any individual is 5, then the average will be 5, the ATT will be 5, the ATU will be 5, the local average treatment effect will be 5, versus heterogeneous treatment effects. Heterogeneous treatment effects means the treatment effect might be 5 for me, might be 2 for John, might be -1 for someone else, right? The averages will just be an aggregate. It'll be a, it'll be a population average over each individual treatment effect that you're counting. So you can have ATE be different from ATT, be different from ATU, be different from local average treatment effect, all right? So your data isn't going to come with a code book saying instrumental variable. So like when you download a data set and it's got 100 variables, you're not going to have a flag saying that one of them is an instrument, okay? Because instruments are not the characteristics of a data. Instruments are the characteristics of a problem. They're the characteristics of a particular data generating process. So instruments are question specific variables, not characteristics of a variable, in totem. Okay, so something is a good or bad instrument depending on the problem you're using it to solve. All right. Therefore, you can't know if it's a good instrument without knowing something about the data generating process, right? You're going to have a theory about the phenomena you're studying in order to justify using logic and theory about why this is or is not a good instrument. Okay, so I'll just say that there. So sometimes the researcher just knows. Sometimes the researcher knows that something is a good instrument. Okay. And let me get into that. So the best instruments, you tend to think of them first, then you look for the data that will allow you to do it. And what you're looking for is an answer to this question. My covariate of interest is my treatment variable. Okay, so my covariate of interest is my treatment variable. Is there anything that, is there any part of the variation in my treatment that is actually random? You know, humans tend to not themselves behave truly randomly. They do things on purpose, usually to optimize utility or profit. But is there ever anything, any part of your treatment that wasn't due to optimization? This is why you see instruments like windfall, or like basically weather related. Weather is thought to be pretty random, not due to humans making optimal choices, but external events making those choices for us. All right, making those choices for us. Right? If we could just find that random piece, right? If we could just find the random part of our treatment, okay? Think about what that means. That means we have random variation in the treatment assignment, right? And if we have random variation in a treatment assignment, we have the ability to satisfy, to estimate causal effects, IV is such a situation, okay? It's just we are finding the randomness in the treatment by finding a third variable that induced that randomness, okay? Something outside of the closed system of the problem you're studying, something that really interfered with the overall problem you're studying, okay? That's why we often are so focused on natural experiments. Natural experiments disrupt the closed system we're studying. It's just they're somewhat chaotic, and not all of them make good instruments, right? So let's look closely at this. Here's a paper by Josh Angrist, who's a giant in the field of labor economics and causal inference in general, and Bill Evans. Bill Evans, I think, was a Josh Angrist student. I could be wrong. Their paper is entitled Children and Their Parents' Labor Supply, published in the American Economic Review. They want to know the effect of family size on labor supply, but they need exogenous changes in family size. So what they want to know is what happens when a family has an additional child? What happens to a woman's willingness to provide labor to the market when her family has an additional child. Problem is, this is part of the optimization. Both having a child and supplying labor are entangled in a family-related optimization problem. They choose their kids and they choose their work, both based on observables and unobservable covariates. So you can't just compare families with 3 kids to families with 2 kids because of the selection bias problem we discussed on Monday. What if we had an instrument for having a 3rd child? Then we could use one of the IV instrumental variables, estimators, and isolate that causal effect of the 3rd kid on labor supply. What makes a great instrument for having a 3rd kid, 3rd child? All right. What makes a great instrument? Okay. Well, what if I told you that if the first 2 children born were the same gender, you were less likely to work? Okay, notice what I said. Notice what I did not say. Notice what I said. If you have 2 boys, you are less likely to work. Mothers are less likely to work. 2, if she has 2 girls, mothers are less likely to work. Compared to who? Compared to families with a boy and a girl. Weird. Weird. Why would the gender of the first 2 kids matter for work? Okay. Because in the United States, many families want at least 1 boy and at least 1 girl. So if they randomly had 2 boys, many families will have a 3rd child trying to get a girl. Same with 2 girls. Notice the elements of this instrument. 2 boys shouldn't affect work unless 2 boys causes you to have a 3rd child. And biologically, there's a 50-50 chance of a boy or a girl, so the instrument is random. The instrument itself is random. Random instruments make for the best instruments. They are easier to defend. They are easier to defend. On its face, so this is something I want to kind of put in your head. This is my own personal rule that I follow for thinking about a good instrument. I think an instrument is good. I think it is a good candidate. Okay, this is what I mean. Typically, if you find a variable to not easily explain an outcome logically, it's probably a good candidate for an instrument. Why? Why? Because the less logical it sounds, the more likely it is that it's a natural experiment. Okay? The stranger variables tend to be variables that have no relevance for explaining your outcome. And remember, it's the things that fit with the outcome logically that are creating endogeneities for us. We know we are missing important variables from our analysis, from our data, right? Those are the ones we understand. They are logical. They fit with the outcome. Good instruments are irrelevant for explaining the outcome. They just explain the treatment. Okay, that's the thing that you want to keep in mind. And that makes them usually strange sounding. Okay, so instrumental variables strategies formalize the strangeness of the instrument, which is the inference that's drawn by an intelligent person with no background in statistics. You need more information, in other words. Otherwise, the layperson can't understand why gender should have anything to do with working. You have to know something about families in order to make sense of that claim. Okay. So I'm gonna go out on I'm gonna take a chance here and share music from a song. Two of my favorite rappers are Kanye West and Chance the Rapper. And there's a song on the album Life of Pablo by Kanye West called Ultralight Beam. And there's this line by Chance the Rapper. Chance the Rapper sings has a lengthy section on that song where he sings. And this is just 2 lines from the song. He says, so let me write this down. So Chance had a popular song a few years earlier called Sunday Candy. Chance also is close with Kanye. They're both from Chicago, and Chance admires Kanye a lot. Okay. And obviously, Kanye is one of the most famous artists in the world. Right? Okay, let's keep that in mind. Here's what Chance says. I made Sunday Candy, meaning I wrote that song Sunday Candy. I'm never going to hell. Right? Made Sunday Candy, never going to hell. Met Kanye West, never going to fail. Right? So I'm going to say something. What in the world does making Sunday Candy have to do with Chance's belief that he will never spend any time in the Christian afterlife in hell? There is nothing in Christian theology or Jewish theology or any theology that says a song can be responsible for one's afterlife. So how in the world is this logical? This song doesn't make sense when we think about the things that cause a person to spend eternity in some location in any religion, right? Songs do not belong in a regression explaining hell. Hell equal A plus B X plus C Sunday Candy plus E. Probably C equals 0, right? Probably C equals 0. Doesn't really make any sense. So what if I told you, what if the song went like this though? I made Sunday Candy. My old pastor heard it, invited me to church on Sunday. Now I'm never going to hell. This this 3 lines actually makes sense for a religious person's beliefs, at least. It is common to believe that religious participation can influence one's eternal life, right? Regardless of whether someone else believes that is fables or reality, at least the theology exists. That's a common belief. Hell equal A plus B, church plus C, X plus E. In the structural model of hell, B is not 0, right? Sunday candy still doesn't belong in the regression, and it isn't even in the E variable. It's completely irrelevant to the hell equation, but it is not irrelevant to the church equation. Church equal A plus events plus U. And events can include hearing a song, reminding someone to invite you to church. Okay, that's what an instrument is. That's what a good instrument is. Doesn't belong here. Okay, so notice the instrument doesn't belong in this equation, but does belong in this equation logically. Not statistically, really, logically. All right. So because Chance's statement did not make sense to us until we filled it in with more information, that is why it is a good candidate for an instrumental variable. It does not, his song does not belong in the hell regression, the hell structural regression model. Right? Ask any theologian, and they will tell you that making a song has no bearing on whether God likes you. I'm being kind of facetious, but you know what I'm saying, right? It's irrelevant. But just because it is irrelevant for hell regressions does not mean it is irrelevant for church regressions. It shifts the treatment, in other words, not the outcome. All right. And that's the diagram for it. Sunday candy changes hell. Sunday candy has nothing to do with the otherwise unobserved determinants of going to church or going to hell. And by changing church, notice church now changes. Now we can estimate the effect of church on hell. Now, all that the instrument is doing, the instrument is only shifting church around, which allows us to estimate the causal effect of church on hell. It does not tell us anything about Sunday candy's effect on hell. By assumption, Sunday candy is irrelevant to explaining hell. It does not connect to hell directly. Notice no arrow between Sunday candy and hell. 2, it is not connected to the confounders. You notice no common cause from you and Sunday Candy. So there's nothing like this, for instance. Right? They're not connected. That's what makes it a good instrument. Versus this one. Remember what he says? I met Kanye West. I'm never going to fail. Well, think about this one. Think about this sequence of events. Is it strange, like Sunday Candy had been for explaining how? Not really. Success equal A plus B, Kanye plus C, X plus E. If I told you that I became famous because Steven Spielberg saw me at a restaurant and cast me in a movie, would you be surprised and think that's illogical? Spielberg can't make a person famous. Of course not. Of course, Kanye West could make Chance successful. He has many ways to do it, including letting him sing on this song, right? Meeting Kanye West is not strange enough. It actually is perfectly logical in the structural equation of success. So it is not a good instrument because it is likely correlated with E, or it just belongs anyway. Here. Kanye West can directly affect success. Kanye West could have a common cause. Right? Anything like that? Anything like this? Either KW success or common cause between KW and you will violate the identifying assumptions for IB to be a valid instrument. Okay. So what I usually have built into my brain is this automatic test. Does the instrument seem strange with respect to the outcome? If it does not, I tend to be skeptical of the instrument. If it does seem strange, I am then a little bit more open-minded with where the author is trying to take me. Okay? Where the author is trying to take me. So, is our instrument highly correlated with the treatment? Right? That's referring to this right here. Okay? Are random elements within the treatment? That's referring to this. Is there anything in here that ever changes randomly? That's what you're trying to figure out. You are trying to ask yourself, is it ever possible that the treatment variable changed because of something random, not because of some optimization system that it fits into? Okay, trying to figure out what that randomness is. Is the instrument exogenous? That means no arrow here. That means no common arrow. Could the instrument affect outcomes directly? Could the instrument be associated with anything that affects the outcome directly? That's the kind of things you want to be thinking about. So let's look at our let's look at the two-stage least squares. Let's start looking at some estimators. Okay, let's start looking at some estimators. So we're going to have an estimator. We're going to have a structural model of schooling. Okay, and Y is going to be log earnings, S is going to be years of schooling, and A is going to be unobserved ability, and then V is going to be the error term. V is going to be the error term, right? And what we want to know is there ever a situation where a person gets more schooling than someone else because something random happened to them, right? That's the thing we want to be thinking about. But right now, this delta term represents the ATE. It's the average causal effect of schooling on log earnings. It can only be estimated, though, if we also have data on ability. Okay. What we're going to do is we're going to assume that we don't have A. Okay, so what we're going to do in the next steps, in the next slides, we will assume we don't have A in the data. 2, S is correlated with A. 3, Z causes S to change. Okay. All right, so let's go through it. So we're going to write down a covariance between Y and Z. So Y is earnings, Z is some instrument, right? I'm going to write down the definition of covariance, which is going to be, I'm going to write down the definition of the equation. So look, the equation was alpha plus delta S plus gamma A plus V. And I'm going to put, instead of Y, I'm going to put the definition of Y in here, okay? Then what I'm going to do is I'm going to rewrite my covariance in terms of its definition, which is the expectation of products minus the product of expectation. So covariance, AB equals expectation AB minus expectation A expectation B, right? So that's the definition of a covariance. So that's right here. All right. Now what I'm going to do then is I'm going to distribute these terms. So I'm going to distribute this one. I'm going to distribute this one. Let me just give you an example of what I'm doing here. So we'll just take one of them. Expectation AZ minus expectation A expectation Z. Okay, see that right there? So that's all I did was I distributed that A term and that Z term, and I get expectation AZ. Then I did it over here too, expectation alpha times expectation Z. Okay, now, since A is a constant, this equals expectation A, expectation Z, minus expectation A, expectation Z, 0, right? So that's just one of the properties of expectation operators. But not all of them are going to do that. Not all of them are going to do that. Let's look at one here. So let's look at this S term. Expectation. It's actually going to be D. Actually, I'll do the whole thing. Expectation DSZ minus expectation DS expectation Z. Now, the constants come out of an expectation operator. So this becomes D expectation SZ minus D expectation S expectation Z. Now that, notice what that is. That is equal to D covariance SZ by definition of covariance that we just did, right? So that's why this right here becomes this right here, right? We do that for all of them. We do that for all of them. Okay, so if I divide both sides by the covariance of SC, now look, here is the causal parameter of interest. Delta is the ATE. It is what we are trying to identify. It is what we are trying to identify. So what if we just divide both sides by covariance SZ? Okay, what if we just did that? Then we would get D equaling covariance YZ divided by covariance SZ minus G, let's see, how do I do it? Covariance AZ, covariance SZ minus covariance VZ, covariance SZ. All right, so write all that out. This is what we're after. Okay, we want this. If I can divide by that, and if I assume that this is a 0 and this is a 0, so notice strangeness means covariance AZ equals 0. Ability was the confounder, and 0 means no arrows. Strangeness means covariance AZ equals 0 and means covariance VZ equals 0, right? No direct arrow from Z to the outcome, okay? The, unobserved determinants of Y, okay? If we could do that, if those are 0, then covariance YZ divided by covariance SZ will identify D under constant treatment effects, assuming those two other covariances are 0. Okay, and that's a simple estimator. That's an estimator. Covariance YZ and covariance SZ are all based on observable data. We have data on Y, Z, and S. If we have data on Y, Z, and S, then we can identify D using this ratio. Okay, using this ratio. This ratio is called the Wald estimator, attributed to, I guess his name was Abraham Wald. It's called the Wald estimator. All right, so there it is. Now, let's look at what this is called. This right here is called the reduced form, and this is called the first stage. Now, they have strange names. Why these strange names? It's because instrumental variables is around 100 years old. And there was systematic research done on it in the 1920s by Yale's Cowles Commission. And they used these terms, reduced form, structural, and first stage. But in the Wald, we just use those equations and for easier reference, call them by those old Cowles Commission names. They are admittedly odd names, but they're common. Okay, they're admittedly odd names, but they're very common. Now, IV estimator will be, so this right here is the true effect. And this is the estimator. So look real quick. Delta IV, that's the walled estimator. Delta, that's the causal parameter of interest. These are not the same thing. Delta AV only equals delta if certain assumptions hold. But you can always calculate delta IV. It just may not be correct. All right? Because it's just a ratio of two numbers. So the IV estimator is consistent if the IV assumptions are satisfied. So we can put back in here the covariance that we did here, put in that alpha, all those terms. Sorry about that row here. That's a mistake. That should be delta. And then divide it by schooling, divided by this term right here. We get all these three. We need for this to be 0. And we need for this, in order to divide by something, the denominator cannot be 0. Cannot be 0. If it's 0, then the ratio is undefined. So we need for S and Z to be related to each other statistically. And we also need those zeros on the other covariances. S is the treatment. Correct, Holger. S is the treatment. S is years of schooling. Z is not the confounder, though. Z is, let me show you the drawing for confounders. So you've got Z, you've got U, you've got S. Actually, this should be A, got Y. So we've got this, okay? So here, A is the confounder because it causes S and Y. And that means S and Y are spuriously correlated because of A. Z is the instrument for S. It is a good instrument because it causes S. 2, it is independent of A. Three, it does not cause Y. It is correlated with Y via S, but it does not cause it. Okay? Does not cause it. And if you have all three, then you can identify delta. The reason you can identify delta is because if you have all three of these, that's 0, and that is not 0. You can take that ratio. Now, applying those assumptions, when we allow n to go to infinity, the probability limit IV is on average equal to the true effect. Okay, so we need these other assumptions to be 0, right? So in the limit, if Z is a good instrument, in the limit, that's a 0, and we get the true effect. Okay. Now, when this is 0, we call this the exclusion restriction. means those covariances are zeros. Okay, that's called the exclusion restriction. And this is called the first stage. First stage. So we need for delta IV to be a consistent estimate of delta exclusion first stage, non-zero first stage, or strong first stage. So let's look at the two-stage least squares estimator. Two-stage least squares estimator was not the first IV estimator, but it is the most common that I've ever seen. It was developed by Thiel in 1953 and Bassman in 1957. This is before the internet, so there was no working paper series. So these guys did not know that they were both working on it. They didn't know that they were both working on it. They published it independently of each other. That still happens, obviously, but now you don't tend to see both of them getting published. Usually whoever comes first will win, and you'll have more of these arms races. But back then, you know, they both discovered it independently. Same thing happened with calculus. Same thing often happens. IV is what I call is a class. IV is not an estimator, technically. It's a class of estimators. It's a group of estimators. I call it a research design. It's any situation like this. This is a class. This describes a general data generating process, but we will choose specific estimators for various statistical reasons to estimate S effect on Y using Z as an instrument. So like, for instance, there's two-stage least squares, Lemel, jive, U-jive, IV Poisson. Oh man, I'm forgetting. There's a Bardic. There's a lot, right? There's all these different IV. There's all these different IV estimators. These are the estimators, but this is the class. This is the IV class of all estimators. Okay, so this these are these specific estimators, but the circle is all of them, right? So you got to keep that straight in your mind. Instrumental variables and two-stage least squares are different. Okay, they're different. Two-stage least squares is a kind of instrumental variables estimator. The walled, yeah, the walled, jackknife, the two sample, there's all these different ones. All right, so I'm going to skip this just for the sake of time. So let's look at the two-stage least squares estimator. All right, so let's go back to the definition of an IV estimator. So remember, this was our ratio from earlier. Okay, this was our ratio from earlier. Now what we're going to do is we're going to move to sample notation, not population expectation operator notation. We'll use the summation operator, right? And the sample definition of covariance, which I show here. Okay, so covariance ZY has a sample analog, and it's the sum, it's the average basically of deviations from the mean. All right, so it's ZI minus Z bar, YI minus Y bar. For the denominator, it's ZI minus Z bar times SI minus S bar. So this is just the definition of covariance. This is just, these are covariance definitions using using sample analogs to the population expectation definition above. Okay. And this right here, this last step, I show in my probability and regression chapter in the mixtape that that these are identical. They may not look identical, but I walk you through this in the book. So if you want to learn more about why they are the same, I encourage you to look in the book, look in the probability section, where I discuss regression and covariance. Okay, so it's the same thing, right? It's just got to do with the nature of products of random variable values from their means. That it's just a mechanical equivalence, right? Now what I'm going to do here is, because I got y right there by itself, I'm going to leave these two alone. I'm going to leave this alone, but I'm going to substitute in the true value of y. Remember what y equaled. Would you expect covariance zy to be low? Not necessarily, Holger. That's a good question. It doesn't have to be. The covariance can be high because it's just measuring correlations. And the correlation between z and y could be strong depending on that first stage. Depending on that first stage and depending on sy. You know, if the first stage is strong, then it's highly correlated with S. So they're moving together. And if S cos y is strong, it is, you know, strong, not the best word, 2, then when z changes, there will be detectable relationship with y, but it won't be causal, not directly. It's mediated via the S variable. Okay, so you don't, what this means is you really can't learn a lot from the reduced form about things like, you know, causality. You can estimate it, and but you can't rule out, you know, you can't determine exclusion. That's what I should say. You can't learn about things like exclusion. You can estimate it, but you can't determine exclusion by running this covariance or its regression counterpart. All right. All right. So I'm gonna on the next slide. On the next slide, I'll substitute the equation for y for the value of y. All right, so let's see me do that. All right, so there it is. Okay, there it is. I got the eta term in there. Now what the eta term is what I did was I rewrote this earlier here. This is the causal model, eta. Okay, eta is going to have ability in it and all that stuff. So I'm going to rewrite that causal model. Okay, I got this first stage regression here. And then I got a second stage regression. Let's hold off on this one for now. Okay, this is the reduced form. Write it in. All right, so I replaced y with its linear model. Didn't do anything with the denominator. Denominators, notice, is staying the same. Now, why is it going from this to this? Why is it doing that? All right, well, look at what's different here, right? let's look at this. Okay, one of the properties of summation deviation from a mean. Sum zi minus z bar equals 0. Okay, so that's a property of deviations from the mean. Some constant zi minus z bar also equals 0. Okay, so sum alpha zi minus z bar equals 0, which is why the alpha has disappeared. I applied zi minus z bar to this and it deleted it. Okay, so it's gone. Now I'm going to apply zi minus z bar to delta s. Okay, so this is going to be sum d zi minus z bar si. This does not equal 0. It's the deviation from the mean equaling 0 property of summation operators doesn't carry over when it's the product with another random variable. It does hold with constants, but not random variables. All right. So when I do that, I'm going to get instead, look what I'm going to get. Sum, actually it's going to be delta sum zi minus z bar si divided by sum zi minus z bar si. All right, remember this, right? There it is right there. Zi minus z bar si, zi minus z bar si. Notice delta sum zi minus z bar. Look at this. So what do you see here? You see this term and this term are the same. So that means that this equals delta, because numerator and denominator cancel out. There it is right there. All right. Now, what about this stuff? What about this stuff? All right. So then we go sum zi minus z bar eta I divided by sum zi minus z bar si. Okay. Now, if exclusion restriction is true, then z is independent of eta. And in large samples, it'll equal 0. Okay. But you need large samples. So there's something subtle here. Technically, IV is biased by that second term. IV two-stage least squares is a biased estimate of delta, but it is consistent, which is a large sample property. Technically, n going to infinity. All right, it's an asymptotic property. All right. So calculate the ratio. We've got here, we're going to go back now. It's back up again. All right. So we're going to back up again, starting over. Now we are starting over again. Starting over again to show two-stage least squares. Mechanics. How it actually, two-stage least squares is actually not going to be the ratio, right? Not going to be the walled ratio. It will be something somewhat more exotic. All right. So we're going to go in steps. Step 1, write out the ratio. Step 2, multiply the ratio by variance Z, variance Z. In other words, multiply the right-hand side of the expression by 1. Okay. Now look at this. When I rearrange this, step 3, rearrange as scaled covariance divided by scaled covariance. What is a scaled covariance? Scaled covariances, where the scale is a variance, are regression coefficients. They're regression coefficients. Okay, that's the definition of a regression coefficient. This right here, this scaled covariance is equal to y equal a plus pi z plus u. Okay, that's what that is. And then this one is s equal g plus rho z plus e. Okay, and that's here, right? That's the that regression coefficient shows up here. That regression coefficient shows up here. So we can express the walled estimator as the ratio of 2 regression coefficients from 2 regressions. The reduced form regression, numerator, and the first stage regression, denominator, coefficient on Z in both. Okay. And what we're going to do, we're going to just go through all that we'll do now. Now we will just go through simple algebra and manipulation to show what mechanically one does when estimating with 2-stage least squares, right? It's all that we're going to do. It's all we're going to do. So let's look at that. So we're going to rewrite rho hat. We're going to rewrite rho hat here, okay, as that. And then I'm just going to multiply both sides by the variance of Z. So it's just going to be rho hat times variance of Z equals the covariance of Z and S. All right, so I got this. Okay. Here. All right, so that's that walled estimator. Here's walled. Okay, there's walled. Times 1. There's the 1. Okay. And notice from the previous slide, rho hat. Remember what rho hat covariance was. Look closely at that. Okay. Rho hat variance Z. Rho hat, oh, I actually did here. Covariance ZS. Covariance ZS is equal to rho hat variance Z. So all I do is I replace covariance ZS equaling rho hat with equaling rho hat variance Z here. Okay, when I do that, I get rho hat squared variance Z. Now I rewrite my ratio by I don't exactly know the right word. Here's how it is in English. By pulling the constant into the covariance and the variance terms. Okay, so the covariance term just becomes covariance rho hat on Z, and the variance term just becomes rho hat squared, just becomes variance rho hat Z. Okay, it's just going to be, you know, when you have a constant, it's going to come out as a squared. It's going to be by itself in the interior. It's going to come out as a square. Covariance is just going to be by itself in the on both sides. Okay, now look here. Question. What is rho hat Z? Let's see. Okay, let's see what it is. Right, so here is the S equation. All right, this is the first stage. Here's the first stage. Here it is, an estimated first stage with fitted, you know, values on the covariates. Okay, and then we end up with S hat equaling gamma hat plus rho hat Z. Now, the constant will disappear in a covariance because remember, it's expectation product minus product expectation, and constants will just be itself minus itself. So they'll delete. So we'll just have, instead, what we'll have is rho hat Z will equal S hat. So this rho hat here is actually equal to S hat, which is a first stage regression. So what this implies is the logic of two-stage least squares means that estimating the two-stage least squares model has two stages. One, get S hat by estimating the first stage. S hat is the predicted schooling using the fitted values on all the instruments from the first stage regression. Two, okay, the IV estimator using two-stage least squares, though, is a regression coefficient on Y equal delta S hat plus U. It's a regression of Y onto the fitted values of schooling from where now the variation in schooling is the variation caused by Z. We have found our randomizing schooling variable. The only variation left is the part explained by the instrument. Okay? So there is less variation in schooling now, which should cause standard errors to rise in smaller samples, definitely. But this is the two-stage least squares logic, you know, statistical logic. It's slightly different conceptually than the walled estimator, which is purely a ratio. It's purely a ratio. This is two stages with fitted values. I tend to think about the intuition of two-stage least squares in terms of two-stage least squares, but many of my friends think about the intuition of IV in terms of ratios walled. They're both the same. right? We started with the ratio to get the two-stage least squares estimator. So they're not different, but you know, we often use either of those intuitively to better explain IV estimation to our brains and others. Okay, that's all I'm trying to say. There's the proof. Okay. Estimation with software. You could manually estimate. You could manually estimate two-stage least squares because it's literally two stages. You'd estimate the fitted values of S in a first stage by regressing S onto Z. Then you'd use the fitted values of S in a second stage regression by regressing Y onto S hat. Problem is, the standard errors in the second stage would be wrong because it wouldn't take into consideration that your random variable was estimated. So you can do it manually, and it can be useful to do it manually. But when you are presenting your main results, it should be estimated using a software, a two-stage least squares software package. In Stata, it's got many names: IV Reg 28, IV Regress, IV Reg HDFE. There's several. Okay, so Holger says, what is the difference between first stage IV, two-stage least squares IV? I've actually never heard of first stage IV. I don't know what that is. And I've actually never heard the term two-stage least squares IV. There's two-stage least squares. That's all I've ever heard. Two-stage least squares IV. Oh, sorry, Holger, you said two-stage least squares IV. So two-stage least squares IV is what we just went through. So, you know, two-stage least squares IV estimators are is the estimator I just discussed. Sometimes people will talk about the reduced form as the reduced form IV regression. So what is that? Y onto A plus Z. The reduced form regression just regresses the outcome onto the instrument. Some people prefer it. You'll see it called intent to treat. That's probably how you've seen it. If you've ever seen someone present an RCT, a randomized control trial, what are they doing in the randomized control trial? Think about what they'll, if you see ITT in an RCT, what is it? They're regressing outcome onto a voucher. That's what it'll be, you know, but the voucher probably assigned some treatment. But ITT will ignore the treatment and only use Z. people have opinions. I do not have strong opinions about this. Okay, new interesting, no end in econometrics to the trainer, many thanks. Oh, good, thanks, Susan. Earnings can also be explained by one's experience. Can experience be a treatment variable as well? Yes, it can, Angelica. Traditionally, traditionally, the earnings regression that we are estimating in this example, it's called a Menser regression. Jacob Menser ran the human capital workshop with Gary Becker at Columbia University for a really long time. And a Menser regression typically looked like this: earnings, education plus experience plus you. So both are measures, but different kinds of human capital. So it was the human capital workshop, and they were obsessed with estimating the parameters on human capital measures like education and experience. But in our earlier example, but an instrument can be a good instrument for education, but not necessarily experience. Just something to remember. Experience is different than education. So the candidate instruments, for one, may not be the same as the other. Okay, you basically have to pick good instruments for each endogenous variable. Sasha says the ITT is a more conservative estimate on it. Yeah, well, it's does it underestimate it? I understand what you're saying, Sasha. I am not positive about the direction exactly. That part I'm not positive about. If I had more time to think of it, you're probably right. You're probably right. I attenuate. Yeah, I think that's probably the right word. The way that I think of the ITT, I think of it a little bit differently. I will show you in a minute that with heterogeneous treatment effects, actually, let me say it again. IV requires, with constant treatment effects, two things: strong first stage, exclusion. ITT just requires the instrument be random. So sometimes researchers really are not comfortable claiming exclusion. Random instruments and exclusion actually are not the same thing, as I will show momentarily. Exclusion is actually harder to defend than randomization, ironically. If you have a random number generator making your instruments, you know the instrument is random. That doesn't guarantee exclusion. That does not guarantee exclusion, interestingly. So some people will just report ITT because they don't want to defend exclusion or feel they can't. So that's one reason I kind of see ITT presented, is that there's fewer assumptions associated with estimating the causal effect of an instrument. It's just that the interpretation of the ITT parameter is technically not the same as the interpretation on an IV model. An IV model will report the causal effect of the treatment, not the causal effect of the instrument. It's kind of strange. This is kind of a strange way to talk. So when we have an example, hopefully it makes more sense. Okay. Melba says, I've seen papers that use several instruments for one endogenous variable. How does that work? Do the instruments need to be independent of each other? They have own arrows connected to the endogenous variable, but no variable. With multiple instruments, the assumptions for them are the same as the assumptions with one. Their relationship to each other is irrelevant. It's their relationship to confounders and structural error terms that you have to focus on. Is ITT? Yeah, Angelica, exactly. Awesome, Angelica, thank you for saying that. So ITT would be like this. Hell, Sunday candy. IV would be like this. Hell onto church, where Sunday candy was an instrument for church, right? IV allows you to know the causal effect of some scientific or policy relevant treatment. You know, Nigeria is not going to pass out vouchers they will build schools, right? We want to know the effect of schools, not just the ITT of Y and Z, but sometimes you may not feel like you can recover. You can recover the effect of S, even if you have a random instrument. See, remember, independence is sufficient for identifying causal effects. So if you have a random instrument, you can estimate the causal effect of that instrument. And it's going to tell you something about the treatment. It just technically is not the B parameter in that first equation, right? Which is what Sasha means, I think, by understating the effect. It's different, even if it is relevant and can, with some work, help you understand the treatment better. Okay. Okay, so in R, it's called IV reg, and in Stata, IV regress two-stage least squares. Right. So 9:15. Let's just keep going because we've got a little bit of some work to catch up on. That took a little bit of time. I wanted to make sure we covered that as exhaustively as we could. What I'm going to do is let's take a 5-minute break. Let's take a 7-minute break. Let's come back in 20 minutes on the hour. All right. So we'll take a 7-minute break and we'll come right back just to give us some rest. All right. I'll be right back. All right. So we need to talk about, since the IV has these two elements to it, it's got the first stage and it's got the exclusion restriction, then we really need to discuss them a little bit more in detail. I kind of was discussing exclusion with, by discussing all the, those arrows and Kanye West and strangeness and all that stuff. That was at least trying to explain the intuition of exclusion. But now we need to talk about the facts about that first stage, because it turns out that first stage is really critical. Now, I only have 35 minutes. Can I just real quick see something? Yep. All right. I think we should probably just conclude with first stage, and I'll just do it my full lecture on weak instruments. So a weak instrument is one that is not strongly statistically correlated with the treatment in the first stage. And it can happen if the instrument is independent of the treatment, if the instrument is really got, if the treatment really is not a function of the instrument, then that will be weak by definition, because they're completely independent of each other. Or they can be strongly correlated with each other, but the sample is too small to have enough power to pick it up. Okay, so you got these two issues that you have to kind of contend with, which is why part of the reason why it's important to really have large samples. So if you have a weak instrument, then the bias of two-stage least squared, the bias term of two-stage least squared, actually centers. That term centering, I struggle with a little bit, but it's centered. I can show it algebraically on the bias of the OLS term itself. So whatever that bias of OLS is, two-stage least squares bias, the weaker the instrument is, it's going to be centered on it with larger variance. So we knew this was a problem, but it got into kind of sharp focus after this paper in 1991 by Alan Kruger and Josh Angrist. And then that kind of led to a response paper, but at the same time, there were some other papers that were kind of interested in the econometrics of weak instruments. And that's just sometimes how it goes. Sometimes like an applied paper or a set of applied papers will just kind of get the attention of a lot of that econometrician theory and kind of build it up a little bit more. And that's what happened here. So there was this early paper wanting to estimate the causal effect of schooling on schooling on earnings. There's actually another paper by Esther DeFlo. I believe it's 2001 or 2004, Indonesia, estimating the effect of schooling on earnings, but it's not IV. It uses schooling construction. This one was IV, and it used a weird feature of American public schools. And in American public schools, you had to attend a school based on when your birthday was. And they used, historically in the United States, a hard cutoff of January 1st. So if you were born after January 1st, you were put in one grade. And if you were born before January 1st, you were put in a different grade. And children have different ages when they start school. And what that means is they're going to have different amounts of schooling when they reach the last year of high school. Some of them will have, by the time they reach a certain age. Now, so if everybody graduates from high school, they'll have all had the same amount of school. But if some people, will have more or less schooling, depending on when they started, when they hit age 16. Why does that matter for age 16? Because in the United States, you could not drop out of high school until you turned 16. You were legally obligated to stay in school until you turned 16. And the reason why that matters is that depending on when you started school, some people will have more schooling than others. Some people will have more schooling when they hit 16 than others, depending on when their birthday is. Okay. So this is something that I have not emphasized yet with IV. I emphasized it with regression discontinuity. Remember, with regression discontinuity, we said very, very important to show pictures. I said you had to show pictures for the outcome, pictures for the first stage, pictures for the Mccrary density test, etc. Right? IV is actually the same way. If you only hear this today, do yourself a favor. Okay, help yourself in the process of trying to get published. Try your hardest to show the let me show me. Try your hardest to show the reduced form and the first stage with pictures. Try your hardest to show that. Find pictures that show the correlation between the outcome and the instrument, and the outcome and the first and the endogenous variable and the instrument. The reason is when people see those pictures and they see those correlations with their own eyes, they're much more likely to believe your result. See, the problem with two-stage least squares, is it's kind of complicated. Statistically, it's a little bit complicated, right? It's a ratio. It's fitted values in a multi-stage regression. That can feel very confusing to a reader, right? Because they might want to be taken slowly through the process. So if you can show a picture visualizing your instrument's relationship with the outcome, as well as the first stage, it will considerably enhance your paper's believability. Okay. And Angrist and Kruger, Josh Angrist in particular, I think he probably is one of these people that is a very good dresser or very good at designing rooms. He's probably got a very keen aesthetic, a very good visual aesthetic. And the reason I say that is because all of his papers have beautiful pictures. I am not an interior design person, and I wear kind of regular clothes. I do not come up with great pictures. So I study other people's pictures pretty closely and try to learn from them. So here's some pictures. All right. So let's look at these pictures real closely and see what we're learning here. What do we got? So what do we have is a bunch of 4s and 3s, right? At the top. Notice we've got 4s and 3s. Pretty much along the way. Definitely over here, you know, you see like this stage, kind of like the first half of the thing, very pronounced. And then when you get over here, less pronounced, right? What is going on with these 3s and 4s? What are these 3s and 4s? Their instrument is a dummy variable based on which quarter of the year you were born. Because remember, some birthdays will cause the student to have more schooling that they have completed before they turn 16 and can legally drop out of school. So let's see if those people born later in the year have more schooling than those born earlier. The later born are those born in the 3rd quarter, 3, and 4th quarter, 4. Notice more schooling is associated with those born later in the year. More schooling is associated with those born later in the year. right? If you're born early in the year, you get less schooling. Why? Those born earlier in the year hit 16 earlier. And so because they turn 16 sooner, they can drop out of school with less schooling. Now, at this time in US history, notice the cohorts. Those born in 1930, 1932, etc. This is a time in US history where dropout of high school was relatively common. Okay, the high returns to education didn't really start until the second half of the 20th century in the US. Okay, be kind of interesting to see if there's a possible study like this that you could do in certain parts of Africa. I've never seen anybody do it, but there might be a way for you to sort of replicate this study yourself, as long as you kind of take seriously some of the criticisms of the study. Now we're going to look at, so that was the first stage. Okay, so let me summarize. This picture is very simple, just graphs the raw data. These are averages per bin, where the bin is a cohort, birth year. Okay, they show 4 data points, but they show them sort of separated out because otherwise they would all be on the same line. So like in reality, this is 1932, right? That's 1932. And so, you know, what you would get instead is, you know, a 1 there, you know, the 2 there, the 3 there, the 4 there. So they made some decision. They made a visual design decision to space out the 1, 2, 3, 4 in ascending order so you could see it. So you have the ability to make whatever design choice you want to make. You just want to pick a visual design that captures the essence of what you want them to learn without misleading them. Be careful of accidentally misleading someone with a picture. Okay? That's all I want to say. They do the same thing again here. Remember, the reduced form, what is it? Covariance, Z, Y. Right? Well, you could show this in a picture easily. Just show the same averages by birth cohort and quarter of birth. See if there is a systematic pattern. If it's systematically the case that the 3s and 4s always at the top and the 1s and 2s are always at the bottom, can't be chance. Right? Chance would kind of have them. Chance would predict no pattern, but here we see a pattern. Here we see a pattern. Notice again, 3s and 4s. Now notice what they're doing now. What design decision? Hollowed squares. Very simple, but because there is less variance in log outcomes, they needed an additional piece of visual information to help the reader see what these authors are trying to communicate, which is that there is a systematic correlation between quarter of birth and earnings. Okay, this kind of fits Sasha's point too, that it's a little attenuated. right? It's, the reduced form is not the same thing as the structural causal estimate. So, you're going to need to make, again, what's the lesson? Pick design decisions that enhance the picture's readability. Goal, make beautiful pictures if you can, or do not make horrible pictures, right? Preferably make beautiful ones. If you can't make beautiful ones, don't make horrible ones. And do not lie with pictures, right? Those are kind of the rules, right? That's the rules and that's the goals. All right, so the causal model, first stage, here's going to be the first stage. So this is the causal model. They want to know delta, right? Years of schooling is just one random variable. Schooling is going to be a function of both covariates and the instruments. The reduced form regression, covariates and instruments. So the pictures, the graphs, this and this. No graphs. There was no graph for this. You do the graphs for these. For this, you do two-stage least squares. Okay? Covariate IV adjusted, the covariate adjusted IV estimator is the sample analog of this ratio, right? So really, again, think back to what the Wald estimator was. Wald estimator was the ratio. That's just going to be pi 1, 1. No, it's going to be pi 2, 1, pi 1, 1 in from two different regressions. All right. So they're going to have 3 dummies. And who was it just a second ago? Melba said several instruments, seen several instruments. Look, Melba, here's several instruments. Okay, so what they did was they made 4 dummies off of one birth year variable, right? The birth year variable listed the exact month of birth. The instrument broke that into 4 dummies. January to March, 1. April to June, 2. July to September, 3. October to December, 4. Okay. They can't include all 4 because of perfect multicollinearity. So they will drop the 4th quarter so that everyone is compared to the 4th quarter. They only did this for interpretation reasons. They could have dropped any of them. All right. Once they estimate this, all right, once they estimate it, they'll get hats on each of these. This will go away. They'll get fitted schooling. And then the second stage will be simply log y. It'll be that regression. Okay. So here's some first stage regression results. You always want here. Let me just say one thing real quick. Important. When presenting your results in table format, always show the first stage as well as the second stage. Readers need to see the first stage so that they can evaluate things like the sign. Does the sign match their intuition? and the statistical significance, because that ultimately relates to the strength of the instrument. All right. So you got to report that. So they reported it. They did a couple of things that are interesting here. First, they report total years of education. All right. Now look, the later you were born in the year, the more schooling that you had. So we can see right here that the people born in the first year had less schooling than the ones born in the fourth year. They get about 1/10 of a year less of schooling. They get about 0.086 less years of schooling. And the third quarter, no different. So again, look at this. Look at how they're presenting this. Notice the presentation of the first stage. Okay. You don't have to do it this way, but you do want to make tables people can easily read and even enjoy reading. All right. You know, one of the big secrets in publishing is that if people find a table hard to read, they are more likely to reject the paper at refereeing. Okay, just fact, whether fair or not, that's true. So make beautiful figures, make beautiful tables. What is a beautiful table? One that you like interpreting. It's one that you like interpreting. You like looking at it. You like spending your time studying it to try and understand it. Think about a confusing table that you saw of someone else. You didn't want to spend 1 second reading that table. It was so ugly, right? Tables are already ugly. Do not make them uglier, okay? Now, you might think that this one is ugly, okay? If you think that it is ugly, try to articulate why it is ugly, okay? Find tables that you like, try to emulate them. I can show you my IV table in just a moment. I have code that makes it in Stata. So here we see total years of education falls, okay? Falls for high school graduates. So if you were born in the first year of the first quarter of the year, you're about 2 percentage points less likely to finish high school than those born in the later part of the year. And notice how it's kind of monotonic. 2%, 2%, 4%, 0, right? I'm going to ignore this other stuff. All right. So they're going to estimate a very, very, very simple IV model without a lot of controls. Okay. Years of schooling, log earnings regressed onto years of schooling. 0.07 using OLS. This means OLS interpretation. Every year of schooling is associated with a 7.1% increase in earnings. Okay. Two-stage least squares, two-stage least squares, or T-stage least squares. Every additional year of schooling causes 8.9% increase in earnings, slightly larger. You ever seen a good example of the IV estimates in graphical form? Yeah, not so much the estimates, Sasha. I have seen really good pictures of, no, I haven't actually. I cannot think of a good example of the IV estimates. Usually, and I don't know if this is a rule, in my experience, graphs will be used for first stage and reduced form. Some creativity is involved doing this. Okay, not all you have that you may have many different ways you could do it, right? So there could be many different ways to present these to design graphs like this. But the tables will usually be where the numbers from the actual estimators are presented. But if you can make something in a graph instead of a table, to be perfectly frank, do it. People love pictures. Okay, they love them. They love pictures. And in my opinion, people could see the same information in a picture and in a table, presented differently in those two separate mediums. And I bet that more people will find the graph convincing than the table. That's my belief. I could be wrong, but pictures speak. You know, in America, I don't know if this is common, but in America there is a phrase: pictures speak 1,000 words, right? And pictures speak 10,000 tables. Okay. All right. So here they have their results. They get bigger effects. Okay. So they could do that. They report all kinds of stuff. They do all these things. But what they're going to eventually do is they're going to use more than just 3 instruments. And this is kind of this is probably the reason that the paper is famous. Okay. Is the fact that they begin to use 180 instruments. Let me read this. To incorporate the cross-state seasonal variation in education, we computed 2-stage least squares estimates that use as instruments for education a set of 3 quarter-of-birth dummies interacted with 50 state-of-birth dummies, in addition to 3 quarter-of-birth dummies interacted with 9 year-of-birth dummies. The estimates include 50 state-of-birth dummies in the wage regression. So the variability in education used to identify the returns to education is solely differences by season of birth. Unlike the previous 2-stage least squares estimates, the seasonal differences are now allowed to vary by state as well as by birth year. What does that mean? That means instead of 3 instruments, they will now interact quarter of birth with all 50 states, all years, to get 180 instruments. So they will regress schooling onto Z1, Z180 or Z179 plus U plus X plus E. 180 instruments. Almost certainly some of those will no longer be highly correlated with schooling. I know that because look, let's go back to the picture. Look at this. You can see the correlation weakens as we go over time. Notice here, it's very strong, right? Born later in the year, you get more schooling than those born early. So for the 1930 cohort, very strong correlation between quarter of birth and years of schooling. Look at this one. For the 1938 cohort, almost no correlation between birth, quarter of birth and schooling, right? So they now have as instruments variables that have almost no predictive power on schooling. Why does that matter? That's what we will see. Concretize. Angelica, can you tell me what concretize means? I'm not familiar with that word. I apologize. Concretize. What's a concretize mean? Yeah, you can't, Angelica, you can. So you have ways. There are definitely ways to test the validity of the first stage assumption, which is what this section of the lectures are about. How do we assess that that an instrument is strong? Okay, that's the first thing. But testing the validity of the exclusion restriction is much harder. Usually, in my opinion, you will need to argue for exclusion based on logic and deep familiarity with the thing you're studying. There are tests called over-identification tests, but they require multiple instruments and strong assumptions about those instruments beyond exclusion. One of those is assuming constant treatment effects, among other things. So if you aren't comfortable making that assumption, then you can't even use the over-identification test. And if you have one instrument, then you have no choice but to argue for exclusion based on logic, economic theory, and your own familiarity with the subject. That means you are also open to someone else using logic, economic theory, and their own familiarity with the subject to argue exclusion does not hold. And this can be very frustrating for you because you have to listen to these fools. I mean that kind of nicely, but it can be a little frustrating because they haven't spent nearly as much time studying it as you, but you know, it's free to offer a criticism. Yeah, it can be a little annoying. So, but you got to tolerate them. So you got to, so really, you know, with arguing for exclusion, the burden of proof, the burden of proof for exclusion is on the author. So you have to really make a very strong, compelling case for exclusion. And it can be very hard. And for that reason, many people can be biased against believing instrumental variables. Many people, as a rule, feel that exclusion cannot be defended. Cannot be defended. I personally find that to be absurd. You can always tell a story where exclusion holds. To assess whether exclusion holds in your project requires knowing something about your project, about the thing you're studying. Okay? But it's not a fair world. And referees are more than happy to reject a paper because they used what is called in America a smell test, meaning they didn't like the argument you made for exclusion. So it smelled bad to them. So do not take it lightly, you must make a strong case for exclusion in the papers and the presentations that you write. You cannot simply say, assuming exclusion holds. Why should I believe exclusion holds? Convince me. This is hard work, but it's essential to using IV. Okay. They want me to show there's no reverse claim. Yeah. There's all kinds of stuff like that, Angelica, that you're susceptible to. Absolutely. I mean, reverse causality. Absolutely. You're going to have to argue that you've got to convince them that the instrument is exogenous, that exclusion holds. Does the Heckman selection model belong to the IV family? No, but that's a good question, and I don't know if this is a good answer. Technically, the selection models of Heckman are usually described as control functions, not instruments, although they can also be, I think that they can also be thought of as, well, see, technically the Heckman sample selection problem historically was identified off of functional form assumptions. What was it? You used that inverse Mills ratio off of like a standard normal distribution of these products, something like that. So it wasn't historically truly an IV estimator. It was kind of its own novel estimator. There's a class of estimators called control functions that you normally teach it now, but sometimes you will use instruments in order to kind of instrument for selection into the treatment or the sample itself. But I typically kind of think of them separately. Okay, so let me just say this one thing. So they do, why did they do this? Really, the reason they did it, the reason why they did this 180? They didn't like these standard errors. That's why they did it. The main reason they did it was they felt that this was not precise enough. Okay. They wanted more precision in their IV estimate, so they used more instruments to get more variation in schooling. Okay, that's what they did. Problem is, many of the instruments that they included are not highly correlated with the treatment. Okay, that's the problem. So they do it, and we get this, here we get the same thing every time. They group their OLS the same every time, and they're just reporting different specifications for two-stage least squares. So here, this one two-stage least squared has a much smaller standard error than the one we saw a minute ago, 0.016, 16 versus a 9. Coefficient's gotten bigger also. And they go through all these different specifications. Okay. All right. So tomorrow, it's 10 o'clock, or it's time to call it quits. Tomorrow, we'll finish up IV. We'll go into difference and differences. But the first thing that we'll do tomorrow is we will discuss this problem of weak instruments mathematically. That's what I'm going to do. So tomorrow, I'm going to walk you through why IV bias gets worse when you have these weak instruments, and why that is itself a major problem. The good news is, it was either Melba or Angelica. The good news is you can test for weak instruments. That's the one you can test for. There are statistical tests. So that's good news. That's controllable. It's exclusion that you're arguing with logic. First stage, you're not. All right. So I'll see you guys tomorrow. Y'all have a good evening. And thank you for all your great questions. And I'll see you tomorrow.